My my pleasure and honor to introduce today's speaker, Lætitia Delmau. She is a radiochemist, scientist, and a distinguished member of staff at Oak Ridge National Laboratories, and is a 2024 winner of the prestigious Glenn T. Seaborg Actinide Separations Award for her contributions to actinide separations. She received her PhD in physical chemistry from the University of Louis Pasteur in Strasbourg, France. And then in October 1997, she joined ORNL as a postdoctoral researcher in the chemical separations group in the chemical sciences division. She was then hired on as staff member in 2000. She worked with the Critical Materials Institute and the Fuel Cycle Research and Development Program, focusing on isotope separations, primarily using solvent extraction and ion exchange chromatography. As part of her work, she helped develop a solvent extraction process to remove highly toxic cesium-137 from the high-level waste stored at Savannah River site. I guess that's still in CZS process, still being used at Savannah River. She and the rest of the salt waste disposal technology teams received the DOE's Secretary Achievement Award in 2013 for that work. During the past 10 years, Lætitia has been involved in developing new processes for improving the quality and quantity of the production of Plutonium-238, Californium-252, and more recently, Promethium-147. In 2022, she was part of a team that produced Plutonium-238 for the radioisotope thermoelectric generator that's been used in NASA's Perseverance rover it's on Mars. Still working? Or? Her work and for this work, she received the DOE Secretary Achievement Award. So today, she's going to tell us about her actinide separations tailored for Californium-252, Plutonium-238, and Promethium-147 campaigns.
Thank you very much for the introduction, Steve, and thank you very much for having me today, for the invitation, and for allowing me to present the work that I've been involved in the past 10 years. So I've always been involved in actinide separation. This was something that I discovered when I was in high school. And after an internship in a French Atomic Energy Commission near Paris, when I was in college, I decided that was what I was going to do for the rest of my life. So thank you for allowing me to show you what basically my passion is all about. So this is a picture of HIFER. And this building here is where I work. It's called the Radiochemical Engineering Development Center. And basically, the targets are irradiated at the reactor, and they're transported here for chemical processing. And this is what I'm going to talk about today. So the isotope production, it's been a mission for ORNL from the beginning. In 1946, this is where there was the first radioisotope shipment to a hospital for cancer research. 1960s, you may have heard, with all the Promethium releases that ORNL really shipped a lot of Promethium during that time. And this is actually, the 60s was really a time where there were a lot of radioisotope shipments coming out of ORNL. For multiple applications. And today the focus is primarily on isotopes that cannot be produced by other in the private sector. So this is the calcium mass separator. This is, of course, the graphite reactor. And basically, HIFER came to be primarily because of a letter from Glenn Seaborg to the Atomic Energy Commission chairman, it was Strauss, in 1957, basically advocating for making trans plutonium and trans curium elements, and that gave birth to studies with beryllium, californium, and einsteinium. So this is a picture of the high flux reactor. And you have the processing buildings right here. This is building 7920. I said that has some hot cell. And here, this is where the Californium-252 is actually repurified after being produced here. So it's being put in the pools and then taken out to make palladium wires that then are shipped and sold to the private sector. So anyway, HIFER and RDC, 1965, 1966. We're expecting it to continue at least until 2040. And basically that allows us to have a continuous isotope production. As I said, as an actinide chemist, I'm more focused on actinides. I like to play with my actinides whole, even though I started playing with promethium that I call a broken toy, right? It's a fission product. And so HIFER, picture of the core reactor here is here. It's the brightest cold neutron source in the world. Typically, we get 6 to 7 cycles per year. And as I said, for us, it's primary isotope production. I put here a picture of Einsteinium-253. It's just 170 micrograms, but as you can see, it can be self-illuminated. In addition to isotope production, the reactor is also used for neutron activation analysis and also neutron scattering research. So not really knowing, usually when I give a talk, one, it's much shorter, and two, it's usually to an audience who is more familiar with separation techniques. So I thought that I would provide some separation basics. The first one will be solvent extraction and mix of separations. So solvent extraction, the way I explain it usually is when you have a biphasic system like oil and water. If you have a ligand, organic molecule that's tailored to grabbing specifically an aqueous species in the water or an aqueous phase, you can dissolve it in the organic phase. You shake it, and it's going to selectively extract that molecule that's in the organic phase. Is going to grab what you're interested in, and it's tailored, so it's going to leave anything that you don't want in the aqueous phase, but the species of interest is going to be extracted into the organic phase. You separate the aqueous phase away, and then you contact it with something that's suitable that will re-extract into that aqueous phase what you were interested in, and that's how you can accomplish some separation. This is actually an aqueous phase here where we have our promethium, and an organic phase where we have a ligand that's tailored for curium. And I'll explain why later. We want to have a separation of promethium away from curium. Here, this is an organic phase that contained plutonium, but then we put in contact an aqueous phase that allowed the plutonium to be reduced and therefore stripped down. And that beautiful lavender blue is plutonium-3, plutonium in special oxidation state. Well, that can get tedious if you do that repeatedly. And so there's systems called mix assemblers where you have a compartment where you can mix both the organic and the aqueous phase, and then a settler portion where you can have the lighter phase that's going to come out, and then the heavy phase that's going to come out via a different port. And you can have a series of those mix assemblers where you can have continuous extraction with usually countercurrent light and heavy phases. And basically what would be very tedious to do by hand, one batch at a time, you can accomplish with however many stages. And that usually falls into the chemical engineering portion of things. Cation, anion, and ion chromatographic resin. So this is no longer an organic and an aqueous phase. The organic phase is being replaced by a solid phase, and your aqueous phase is now a mobile phase. And this is if you have a water softening system at home, this basically is what's happening. You flow or a burrito filter for that matter, you flow your water through, and the resin is going to grab contaminants most of the time cations, and this is what's happening here. This resin here was actually loaded with some plutonium, and you can see that here there's a band that's greener where we had some transition metals that were mixed with it, and depending on the affinity for the cation with the resin, then that's how you can get some separation. Here it's an anion exchange resin, similar. It's just that you have to make sure that the solution that's being loaded, the species that you want to retain, is in the right chemical form for this. Extraction chromatography, this is not an exchange. It's just a porous resin bead that's filled with an extractant. So it's a little bit closer to what solvent extraction would be. We call that solvent extraction on the bead. So where the solvent here that's trapped can extract selectively, and so you can play with the affinity of that solvent for what you're loading. And here, this is actually a column that has promethium on it that has different color, where you can see that the little pink here, that's the promethium being trapped, and there are other colors underneath. So you can actually do a separation of what you want on the column and then capture during the elution. So when that is being released, different fractions, and that's a way to purify. So on to Californium-252 production. This is, we're about to start campaign 81. So I have been part of just 5 campaigns so far. So this is something that's been going on for a long time at ORNL. So I'm going to give you an overview of what happens. So we're going to start with the high flow irradiation. And I put in darker blue what I'm not really going to talk about, because that's solid state chemistry, and this is really not my area of expertise. But basically, we have targets, they irradiated at high flow. And then, as I said, they come from high flow, and that's where the aqueous processes starts at RADC. So we have the aluminum dissolution. So we have those targets. They're
What's the half-life of California?
2.6.
What's the half-life?
Californium-252 is 2.6 years. So those targets that are represented here, you have aluminum dissolution that's caustic. So only the aluminum and the soluble fission products, typically some of the ruthenium and the cesium-137, are soluble, leaving all the oxide, the actinide oxide, that then are dissolved in nitric acid. And that's when you start the first extraction. That's called the Kleenex process. So basically, it's a batch solvent extraction. We have very large tanks. And the solvent extraction, where you have an organic and an aqueous, basically what we do is the solvent is just for actinide, trivalent actinide and lanthanide. So trivalent cations are extracted. The rest of the fission products typically stay in the raffinate. We discard the raffinate, we strip the organic phase, and that gives us the feed for the next step. So now we have the lanthanides, which we don't want. They're part of the fission products, typically from lanthanum all the way to gadolinium, and we don't want them. And then we have a little bit of americium, curium, and the transcurium element. And for this, we actually go into a very, very, very high chloride medium, where those trivalent, they're so surrounded by so much chloride that they actually form an anion. You would think of trivalent cations are staying 3+, but when they're in 12 molar lithium chloride, they actually make chloro complexes that are anions, and then we use an anion exchange column. And that allows us, depending on the concentration of the chloride, to first break the complexes. So what comes out of the loaded column, first out the rare earth, then we have the americium curium, And then this very, very sharp peak is all the trans-curium elements. Some very small amount, that's why the trace, that is the amount of alpha, is being followed here. So here you have the column volumes, and we follow what's called the alpha trace. They're alpha emitters. For the americium curium, here it's actually, there's so much gamma, the fission products are so radioactive that actually there's a, I would say, a false alpha response, but that allows us to follow this. And, oops, sorry. So, and then, as I said, we break the complexes, and then we use the Californium here. So the next step after that is the hydroxide precipitation. So let me, oh, that's the lithium chloride anion exchange again. That's an actual trace. The rare earth, so the fission products, the americium curium, and then the very sharp peak here. So as I was saying, the next step is the hydroxide precipitation. You see it here. Typically, we add iron to help with the precipitation. And the next step is a cation exchange, is where basically we separate berkelium, californium, einsteinium, and fermium. And I'm not going to go into too many details, but basically we use a column where we have a competition between the affinity of those four trans-curium elements with the solution that flows through. And that allows us to separate, on the front end, you have the einsteinium and fermium, which we keep, and that's primarily for research projects. And then we have the californium right here, some berkelium, and then the trace curium towards the end. So this is when everything runs very well, right? So we can separate this here. We have hydroxide precipitation for the americium curium. Then it's then precipitated with oxalic acid. That provides an oxalate compound, precipitate, that then can be that provides purified curium americium product that then is loaded into a cation exchange resin, and basically that allows us to get the oxide, and that's how you close the loop here. So you harvest what was made by transmutation at Haifer, and you re-inject the americium curium after purification into that loop. However, and that's something, so that's something what I just described is a process that's been in place for many, many, many years. Where I came in is that there are several places where you can have rework. And so in order to maximize the return on investment and where you can actually recover from any process upsets, so you can have solutions that contain californium, but where the curium is low. That's primarily here after this lithium chloride anion exchange, where you have separated the trans-curium elements away from the americium curium. So a little bit here, that's what I put it in dash. Here, definitely, during the hydroxide precipitation. And in red, you have solutions where you still have a lot of curium mixed with the californium. So we had an upset at some point where basically after the solvent extraction, we typically had a holdup of about 0.1%, but in the recent campaign was 6%. So we designed a method inside the hot cell. So this is a picture of the hot cell where we were able to basically flow the aqueous phase. This is a extraction chromatographic resin. So the pores here of the resin are filled with a solvent that allowed us to grab selectively the californium. And so we had a quantitative recovery of the curium and the californium, and that solution was actually perfect to be added to the next step, and the next step being the lithium chloride process, where the rare earth, americium curium, and trans-curium elements were separated. Then again, we also had some rework to do with where we had so low rework solutions here. On all those green solutions were combined, and same kind of column here with the resin. And basically, we were able to recover all the californium, and we're able to re-inject about 6 milligrams. A typical campaign of should have started with that. Typical campaign is we start with 60 grams of curium, and that produces about 100 milligrams of californium. That's a typical campaign. 6 milligrams is actually a noticeable amount, enough to warrant being sent back into the campaign. And then, we also did a recovery of what I call dirtier rework solutions, where we had a higher amount of curium. So separating curium away from californium is not as easy, and particularly when we had a significant amount of curium, and it could actually displace. This column was actually had the right capacity to grab the californium, but was not enough to grab all the curium. So the curium actually came out, but all the californium stayed. So that was just to make sure that we were not interested in recovering all that curium. It could go into the raffinate, but we wanted to keep all the californium. And that was accomplished too. This is something that's going to be implemented in the upcoming campaign. The solvent extraction, the very first step, is done after the oxide is dissolved in nitric acid. So you have a solution that is very high in acid. The next step, the solvent extraction step that has been used up to now, is a cation exchanger. So it's a solvent that has to work at low acidity. You must be at low acidity or it won't work. So we spend a lot of time taking that solution and decreasing the acid so that the next step, when we contact with the solvent to recover the actinide and the lanthanide, can work. So instead of doing that, we've decided to change the solvent, and instead of using a solvent that only works at low acidity, we're now changing to a solvent that will allow us to work at high acidity instead. And that saves us about a week of processing time to adjust the original solution that we need to extract the trivalent actinide and lanthanide from. So, as I said, the impact is to eliminate that adjustment and also recover the lanthanide in low acid. And low acid is also better when you have, with the current system, it's extracted at low acid, but it needs to be stripped at high acid. And then that high acid, again, needs to be evaporated off. So this system is going to, it's not that it's going to give us necessarily a better product, but it's going to be much easier to process and faster. So this is something that was done about 2 years ago. There's a campaign done every other year. I was given about 6% of the whole campaign. So they told me you can play for about a week in the hot cell. And so we designed the glassware. So I don't know if you can see it very well, but basically we had like a humongous separatory funnel. It was about 3 liters. And you can see here the feed or the solution, that the crude solution after dissolution is here with a little bit of orangish tint. And here we have the solvent. So what grabbed the californium and the curium above. And then we air sparged. So the 2 phases were mixed. And then we let them separate. So like oil and water, they would separate. And then the product is here in the clear solvent here, turn that orangish color. And when it's fully settled, so then we could drain this aqueous phase here and keep only the solvent and strip it, and that contained the elements of interest. And this is basically all the different elements. I'm not going to go into it, but basically all these here are the things that we don't want. and that was in the aqueous phase. And basically the Californium here was primarily separated away from the rest in the different, when we took that solvent and contacted with clean solutions that then stripped that solvent. So on to plutonium-238. So why do we want plutonium-238? I'm assuming most of you have seen The Martian, and you must have seen Matt Damon going and digging up the radioactive source and said, do not, but it wants to stay warm. Well, that's an RTG, you know. Plutonium-238, I like to tell people it's the one that does not go boom. It's not Pu-239, it's Pu-238, and it's been used since 1961. Basically, there's nothing to really plug to get power in space. So what you use is the heat of decay of Pu-238, 87-year half-life, and in order to make radioisotope heating units. And next mission, I think is planned by NASA, is Dragonfly in 2028. So more specifically, so Pu-238, it glows red, and we have to be very careful even when we make a few grams inside the hot cell to keep away anything that's plastic, because it will melt if it gets in touch with the container that contains the plutonium oxide. So it's fissionable, but not fissile. That's why I said it doesn't go boom. But basically, what do? We make neptunium-237 oxide targets. The neptunium oxide is mixed with aluminum metal. And then those targets are irradiated at HFR. Capture of 1 neutron, neptunium-238. Very little fissions, but a little bit. And that's why we'll talk about promethium, later on. So there's a little bit of fission products, but primarily capture of neutron and beta decay. So basically you keep the same number of nucleons, but there's too many neutrons, so it moves up to the next element and makes Pu-238. So 100% alpha decay, and this is the number of watts per kilo of decay heat. And as I said, this is what it looks like. That's a pellet, and it glows red because it's so hot. So this is the overall supply chain. There was a stop in the domestic production. There was purchases that were made to countries where we no longer can get the plutonium from. And so when the Pu-238, since it's dwindling down, they started reestablishing the full chain. So basically what happens is there have been some Neptunium-237 made at Savannah River that then has been stored at INL. And then INL then sends the neptunium oxide to ORNL. And that's what we use to restart that. The targets are made, irradiated at HFR. We make the plutonium oxide, we send it to LANL, where they make the RTGs. And I think then it continues on for the RPS assemblies that are also made at INL. So overall, we have the neptunium oxide at INL. At ORNL here, we do all the chemical processing with both the production and also the recycling of the neptunium. The target irradiation is done at HFR, and then, as I said, the plutonium oxide is being sent to LANL. This is a picture of a target, a single target here, when you have several pellets, a spacer, a top cap, but this is what is being sent to both HFR, but also the ATR, the Advanced Test Reactor at INL. ORNL for the past 4 years now, I believe, has been also sending targets to INL for irradiation, and those irradiated targets will be sent back to ORNL for processing. So this is the overall flow sheet. Irradiated targets start here, just like what I presented for the Californium production, where we have the irradiation of the curium targets. Here, the neptunium targets come back after irradiation, and we go through caustic dissolution. So again, the aluminum is removed and the soluble fission products are removed. Then we do an acid dissolution, just like before. And then we use solvent extraction to separate the plutonium away. So there's about anywhere from 10 to 12% transmutation. That's the amount of the percentage of neptunium that's converted into plutonium. So we separate that amount away from the rest of the neptunium and the fission products. And that crude product is purified by anion exchange. And when we have the purified plutonium, then we load it into the cation exchange resin that then is calcined. And that's what makes the plutonium oxide product. So let's talk about plutonium first. So we don't do batch contacts. Everything is done inside the hot cell. And we're using the mix of settlers. So where we have a solvent and an aqueous phase in intimate contact here with some mixing, and then into a settler where we have then the organic and the aqueous phases that are separate. This is what it actually looks like. This is the settling phase. We don't see the mixing phase in the back. And this is an example, just an example of what we have inside the hot cell. So in the first bank of the mixer settlers, we extract the plutonium, and the aqueous phase stays with the neptunium and the fission products that's being sent to a raffinate tank. And then so we have that organic phase that's loaded with plutonium that goes into a second bank of mixer settler, where we contacted with an aqueous phase that you remember that lavender blue plutonium, that's pretty much what happens there. We have a special aqueous phase that will selectively convert the plutonium to a oxidation state that doesn't make it suitable to stay in the organic phase anymore. That then stripped organic phase can be used again, sent back to the first bank of mixer settler to continue processing. So it's a loop that allows us to separate the plutonium away from the neptunium. So when we then have that crude product, we load it onto a column where the plutonium is going to get trapped, but then any traces of fission products, neptunium, we will then be separated away. And for this, we actually, there we go. We actually have a detector at the bottom of the column, and we do what's called spectrophotometric measurements. So basically, we look at the amount of light that comes out, and there we can see a species coming out by their signature, by their light signature, essentially. So, and so we can, oops. We can detect the different species, and that allows us to stop the elution and switch to different bottles when we see impurities and when we see the product. So, and this is actually the example. So this is our big column, and several liters. So we load the crude plutonium product that was obtained from the previous step. And so the resin usually kind of that like yellow, and then once everything is loaded, it loads gray. And when it's finished loading, we send a different type of liquid through, and you see that it's clear at the beginning before the plutonium starts coming out, and at the beginning it's kind of greenish. That's because there's some neptunium impurities still. But then very quickly the color changes and you get the typically yucky brown plutonium-4, but it's purified. And that allows us to have very clean plutonium that then is put onto a different type of resin. And you can see that it's been loaded here. So it's been retained. This is the empty column. I mean, just the resin, plain resin. Goes all the way to complete loading. And then we remove any liquid, so only the resin goes, and then we put this into a furnace. The resin, just like in your oven, right? You crank up your oven greater than 500 degrees, anything that is organic is going to burn off. Well, here the resin is an organic, basically it's plastic beads for all other intended purpose. So those plastic beads are going to go away. And you're left with plutonium oxide. And that's what gets shipped. It's characterized first, then shipped. So in addition to the, as I said, we had here the, I put a big X. The way we purify the plutonium, we used to purify the neptunium too. However, when you have several kilos of neptunium to purify, it takes a long time. So instead, we started, so this is a column that's not plutonium, that's for neptunium. And why did we have to purify the neptunium, right? I mean, it was just some fission products. And so it was primarily because there was a little bit of phosphorus. Why? Because the solvent that we used to do the previous step contains phosphorus, was tributyl phosphate. It's very commonly used in the Purex process, so where you have uranium-plutonium separation. Well, when you have phosphorus in the solvent, the phosphorus tended to follow the neptunium, the degradation product, or the tributyl phosphate, follow the neptunium, and when the neptunium was converted back into an oxide, that made P2O5, so phosphorus oxide, and then those made the neptunium pellets crack. So phosphorus was a no-go. So we were purifying it, and we were doing those big columns for just the purification of the neptunium away from the phosphorus. So the idea was, well, how about using a phosphorus-free extractant? That sent me back 30 years ago when I was working in France, where, of course, France was working on Purex too, but France been trying to depart from tributyl phosphate for a long time. And when I started as an undergrad, that big, that tall, that's exactly what I worked on. I worked on monoamides. So instead of having tributyl phosphate, we've been using an amide. So a carboxylic chain here and connected to a nitrogen with different branches. And basically, these are not new. But the good thing is that they don't have any phosphorus in them. So it's it would be fully incinerable because it only has carbon, hydrogen, oxygen, and nitrogen. And it works exactly the same as TBP. And for us, for our purpose, is that the use of these molecules would not impact what had been developed for the plutonium production with TBP. Basically, it's unplug TBP, plug in those monoamides. And then finally, in addition to what we have here, so as I said, the neptunium gets recycled, but we also inject some fresh neptunium oxide. The problem with, in any case, Neptunium-237 has a 2.1 million year half-life, but its daughter, Protactinium-233, only has a 30-day half-life. So you get in what's called secular equilibrium. So basically you get, even though you make a minute amount, right, 2 million year half-life, in 30 days, you're not going to have much in terms of mass of the daughter, but that daughter is very, very, very radioactive. And unlike the Californium targets, neptunium targets are made in the glove box, so we must remove the daughter away from the neptunium before we pass it on to our colleagues. Otherwise, they would get a massive dose, gamma dose. So for the neptunium oxide dissolution or the neptunium solution purification, we had an original setup where we were dissolving the oxide in a small glass pot inside the hot cell, but it was a couple hundred grams at the time. And it would take about a week, anywhere from 40 to a week. There was no plutonium removal, and we had variable results of Promethium-238. So the dose that we were sending to the folks who work in the glove box was not always optimal. So we had some development set up, and looking at, when you stare at the same pot, over and over and over again, you start thinking, okay, what is happening in that solution, right? We were just taking the oxide, putting nitric acid, boiling it. It turns out that in order to, when you dissolve neptunium, there are actually other side reactions. I'm not going to go into them, but we went from a batch that would be dissolved in between 4 days to 1 week down to 12 hours. And what we have now is that we have about 7 times the amount that we used to have then. We can dissolve in a tank, no longer in the pot in the middle of the hot cell. And we have a dissolution time, so you can dissolve 7 times as much in a fraction of the time that we had before. So these were the challenges that we were able to overcome. The neptunium that is stored at INL that we get every so often to supplement the amount of neptunium that is being converted to Pu-238 contains a little bit of plutonium-238. So we have some limitation on the amount of plutonium-238. That's for the workers who are handling it. And we also have the Actinide-233. So we have these when we recycle the neptunium from a campaign. We have more plutonium-238, as trace levels, but still. And of course, we have Actinide-233. So this is something that was designed here. We are cleaning up the neptunium, but we're not trapping it. This is a cation exchange resin. This is a resin that we would have way too much neptunium to trap it all and then elute it. Instead, we're making it in solution so that the resin doesn't want to touch it. So the neptunium goes through, and the resin only grabs what we don't want. So it grabs the trace plutonium, it grabs the trace thorium, and it grabs completely the protactinium. So we actually can give our colleagues some neptunium solution that's very, very, very clean and does not give them too much of a dose. We were trying this, so this is in cell. The previous one was inside a glove box. And we tried to reuse the resin because there are only trace amounts of thorium, plutonium, and protactinium. And when we tried to reuse the resin, we noticed that actually our performance was getting worse and worse and worse. The protactinium kept on coming back, and it was actually not a problem with the loading issue. It was a reusing issue, because when you load protactinium, and I'm just going to talk about protactinium, and basically the protactinium sticks on top of the column because it does not go anywhere. So you're flowing everything, but the protactinium stays up here. And when you're rinsing, you're moving the neptunium, the plutonium down, but when you really try to strip everything, all the protactinium does is smear throughout the column. And then when you do your next step, well, what it smeared throughout the column starts coming out. So no more reusing. We just use fresh resin every time, and the neptunium is squeaky clean. So this is, again, a picture of when we do a neptunium purification run. You can see that greenish solution, and the column actually looks completely green. That's because neptunium is maintained in an oxidation state of 5, which is beautiful emerald green. And the resin doesn't want to have anything to do with neptunium-5. Neptunium-5 goes through, and the impurities are trapped on that column. All right. So that was the overall flow sheet, and I want to concentrate here, right here. When we separate plutonium from the neptunium and the fission products, I told you that we're going to use something in lieu of TBP, those monoamides, right? So we do another round that separates the neptunium away from the fission products. And this is where the promethium is. In any given campaign, there we get between 100 and 200 milligrams of promethium. And for reference, 1 milligram of Promethium-147 is 1 curium. Within tiny difference between the two, but 1 milligram is 1 curium. The problem is that when we have this big, I mean, a campaign for plutonium is, a large number of targets we're talking about, kilo level of neptunium, hundreds of grams of plutonium. So it's about 100 liters of waste solution that we have to fish out 100 milligrams of something that we want. And also the fission products are not by themselves, right? You're making also a lot of lanthanum, cerium, praseodymium, neodymium. So it's on the tail end of the fission products. So, as I said, we have different ways of making, there's another way of making Promethium-147. You can also make a pure neodymium-146 targets and irradiate it. It's going to absorb a neutron and make Promethium-147. But in our case, we get it from the Plutonium-238 campaign wastes. Why is there such a large interest in Promethium-147? It's a pure beta. Has a tiny gamma, and believe it or not, that 0.002% gamma, we can see it when we make very pure promethium. It's beautiful. Anyway, and it's used primarily from thickness measurement on thin films, and the radioisotope portfolio manager at ORNL told me that was like a $4 billion because of all the cell phones that require certain things in the. Anyway, it's related to cell phones industry, and so having those thin film measurement is very important. So we say that Promethium-147 is obtained during the fission of Neptunium-238, Plutonium-239 during the reaction. When Neptunium-238 fissions, it does not make Promethium-147. It actually makes iodine-147 and lanthanum-147. So isotopes that are extremely neutron rich. And because they're so neutron rich, they're going to go and have beta decays very fast. I think the one before Promethium-147 is neodymium-147, which is an 8-day half-life. The next one is Promethium-147, and it has a 2.6-year half-life. And it decays into samarium-147, which is stable. So it's not that it truly produces that all the other isotopes 147 are very short half-lived, and promethium is the first one that has year-long half-life. So as I said before, when we have fissions, they usually end with the element gadolinium. And the first separation that we do of the 120 liters, we retain everything onto a column. And we do some chromatographic separation in order to separate. We do a crude separation of the cerium-144 and the europium-154, 155, which are very strong gamma emitters. And then we can transfer that to a cave, which is basically one step down from a hot cell, and do the processing there. Or if the doses are low enough, we can actually go to a glove box and do the separation there. And then either we're already in the glove box or we transfer from the cave to the glove box. The goal is to separate americium, curium. Curium and promethium almost have the same chemical properties. You find one, the other one is there, at least for what we have. And why do we have curium, right? I mean, it comes from Plutonium-238 campaign. It's because we have hot cells where both plutonium and Californium campaigns are processed. So you always have a very small cross-contamination of one campaign into the other. It's milligram quantities. But for us, when we only have 100 to 200 milligrams, that makes a difference. So, So this is something that we did in early June. We had that column inside the hot cell where we had the feed tank, so 100 liters. We put that through a column. And all these light blue are fractions that we discarded. So we collected all the raffinate, so what came out of the column, into all those bottles. And then when we did the analysis, we actually realized that our promethium was in all those bottles, 1 liter each. That was, and then all these had primarily samarium and other lanthanides. So we kept those bottles. And then, so what we did next, we took only the product bottles, and the cape was not available. So we did all that in the glove box. So that's a very small column, it's about 15 milliliters column. You can see the difference here in color. This is unused resin. This is resin that is loaded. So we were able to take those 1 liter bottles and push them through. And we had a very good acidic product, very small amount, because again, we're going from liters, very, very small concentrations. The goal is to concentrate, even if it's the crude product, to concentrate our product. So we did this, and then we did a second column that allowed us to remove some thorium. We had some thorium contamination. So, and then we were able to load this onto another column. We do a lot with columns in at the beginning of the process. So we have the crude product, we adjusted it to the right acidity, we loaded it, and I don't know if you can see it, but you see some pink here, and that is the promethium. And that allows us to reduce the volume here. You can see the tint here is actually a mixture of promethium with some neodymium. And so we kept 2 of those cuts, and then the curium removal, that is a step that's done by solvent extraction. We're using some molecule that is designed to separate trivalent actinides from lanthanides. So it's a special molecule that when we do solvent extraction step, we put that molecule in the organic phase, the top, and that leaves the promethium in the aqueous phase. So basically what we do is we start with, promethium and a significant amount of curium. We do a solvent extraction step. The promethium stays in that bottle. The curium goes up into the organic phase, but then we strip the organic phase with some very low molarity nitric acid. So basically, essentially with water. So we get the curium in the bottle. And then we keep this bottle and we contact it again. So it leaves just a little bit of curium, and the curium gets stripped. We reuse the solvent for the next step and the next step, and it goes on until basically the total amount of curium in the system is very low, and the promethium is essentially free of curium. The industry does not want any alpha emitters, and curium-244 is an alpha emitter, and we have very, very, very stringent levels of curium to achieve. And it goes to what we call a beta box, so beta emitter only glove box. And that's where we do the chemical purity improvements. So promethium has some samarium and some neodymium there around. So here you can see a little bit of yellow, that's the samarium, even if it's very faint. And here you see a little bit of green, a little purple, that's praseodymium and neodymium. So once we are free of alpha emitter of curium, then we do more separation where we keep basically the center cut here, and that allows us to get a very, very clean promethium. And this is basically what it looks like, very pale pink as we evaporate it and make the product. So we start with very, very crude product, 120 liters, down to, this is about 30 milligrams of promethium. And this was shipped at the very early September to one of the customers, and it had a greater than 99% purity. This is a collage of a batch that was obtained before the Nature paper, and you can see this side was only 16% pure, the rest was neodymium and it's more purple. And you can see here that was 94% pure, the difference in color. Promethium is more baby pink than purplish. And here you can see it in different stages of evaporations. This is the actual picture that is in the Nature paper. And that's the article is here. And I brought the issue if some of you wanted to see it. And that's it. Nothing that I presented, it's not something that I've done by myself. So I want to acknowledge all my colleagues that are now, other national labs and university. It takes more than just a village. And NASA, the DOE, Office of Science, and then all those other programs that have contributed. Thank you for your attention.
Questions?
What is the heaviest element that can be usefully extracted from high C? What's its half-life?
Okay, the one that is being requested primarily by German colleagues for physics purposes is fermium, einsteinium and fermium. So, and those two were, I think, studied by Dick Hare at the TRL few decades ago. There used to be the campaign, from what I understand, because as I said, I've been at RADC only for 10 years, but they used to have multiple campaigns a year with much larger amounts of Californium being produced. So that allowed them to have more of the einsteinium fermium, but there's a demand. And I think some einsteinium was shipped this year.
What is their half-life?
Okay, the Einstein-253 is 20 days.
Sorry.
But 20 days, I think. But the 254 is longer half-life, it's several months. But I'm not sure what you mean by useful. I mean, it's the demand is primarily for fundamental research. And for fermium-255 is obtained by beta decay of einsteinium-255 also. So you can have different fermium, but they're there in picogram quantities in what we're getting. For the fermium, the einsteinium is more like micro to nanograms.
So beyond that, it's sort of one atom at a time?
Pretty much, yes. I'm not sure, we cannot detect, no. We can detect fermium einsteinium, but nothing after that.
You're not working on a scheme for tennessine yet.
Oh, tennessine is different. Tennessine, you have to have the right targets and the right. We do neutron reactors, not particles.
In the making P-238, this material is thermally hot. As it moves through the process, it seems like you start having problems with equipment degradation due to thermal heat. Is that a problem?
Okay, let me go back. We make sure, so this is for neptunium. There's really nothing, okay. First is solvent extraction. So we keep the concentration of the plutonium in solution low enough. When we do the plutonium cleanup, there's a constant flow of liquid. So there's some heat dissipation. And here, those bottles where the plutonium is being stored for until it goes to the next step of being loaded onto this resin, we keep the caps open. But there's enough heat dissipation. Those solutions don't boil, if that was your question. But for the equipment, no, because there's very small residence time. Here, it's about to go into a furnace anyway, but once it's fully loaded and we put it inside the furnace, because it's insulated, we can actually see the temperature rise inside the furnace, even with all the elements off. But it's quartz columns, so basically it's something that is supposed to withstand high temperatures.
This is probably a dumb question, but they separate uranium in a gaseous phase. So the question comes to mind, were any of the elements was combined with something to form a gas that you could use centrifuge to separate them? Or is that the chemical is much more of a bulk, large separation than a gaseous separation?
Aqueous systems are usually easier to handle. And when I think of gases and separation for gas, it's more for masses, so isotopes, more physics.
Okay.
Here we deal with the chemistry. So whether it's plutonium-239, plutonium-238, there's some plutonium-239 that's also produced by neutron capture 238. We also see a little bit of Plu-240. So they're all there, and as long as they meet the minimum assay of plutonium-238, that's what but we don't try to do any isotopic separations, and that's and again, I may be wrong, but I also associate gas separation as being very demanding in terms of energy and equipment. So
Yeah.
it would not, what we're doing would not warrant that.
With your experience with separations, what do you think of the concept that I keep hearing from people of using large-scale reprocessing of power reactor fuel to produce plutonium or uranium or whatever material we're trying to focus on for a future cycle?
Well, you asking a person who grew up in France, where almost 80% of the nuclear energy is, and the energy is nuclear, and where the decision was made by the government and something that cannot be really reversed, to stick with nuclear energy. Where La Hague has been the reprocessing facility of La Hague, where they separate the uranium, plutonium, with the Purex process.
So successful.
I'm sorry.
You think it's successful?
I think it works really well, and I think this is something that should be implemented here, but it's my own opinion.
The
Yes.
issue in the US is economics.
Politics.
What is what?
It's economics.
It's economics, but I think also it's perception, and also
It's
you have different.
perception, but
There's and proliferation. There's a concern of proliferation, and then you would have to if you separate the plutonium-239 away from the uranium, then you have to guard it, right? And as long as you don't want to make it too pure, because then the level of safeguards goes up and up and up. So it's easier to just keep everything together. The fission products that are there, the rods that come out are so radioactive that nobody would touch them. Well, you can't. But you start separating things, then yes, Dave.
Well, along these lines, the security of proliferation, one thing that struck me as you were talking was you're shipping things from Idaho to Oak Ridge, New Mexico. And, is there a security issue there? Would it be better? Is there a thought, or is there a way to consolidate some of that?
I think they don't want to consolidate. They want to keep different things in different places. If that's my understanding, that I'm beginning to talk outside my my area of. I don't know. But
Your volume, my perception is your volume has been very small compared to anything that would be useful for a weapon or something like that.
But the thing is that it's not really weapon. That's what I said. It's not plutonium-239.
Yeah.
It's plutonium-238. It has, and I'm sure that whoever's taking care of the shipping has looked into that. But I think when you talk about consolidation, I don't know. The only thing that that I know is, at least in France, I know that they don't want the, for the weapons. They don't want the people who do the explosive to be in the same place as the people who make, the fuel assembly or the assembly. I mean, you don't mix. You want to have a very, very large distance between everything. So I don't know if that comes into play here too, but no, there will be we're just ORNL is just as the processing. And Lanol, I know that redissolve the plutonium oxide, repurify it to put it in different, then they have their own process there too.
So ORNL is the only source in the world for the Promethium-147?
Right now, yes.
Yeah, and who are the customers?
Eckert Ziegler, primarily. It's a company that then has, and then they have their own customers.
What do they use it for?
Yeah, what are they used for? Cell phones or?
Well, they're making thin film, detectors for thin film. They're basically, a beta emitter can go through, usually it's stopped by plastic. I mean, different radiations have can be stopped by different things, like an alpha emitter can be stopped by a sheet of paper. A beta will go through a sheet of paper, but then will be stopped by thick plastic. And then a gamma emitter will go through that, but then takes concrete. That's why we use, hot cells. And then you have the neutron. So with the right energy, and it's a pure beta, so you don't have any concerns about the other radiation types, you can actually make detectors where the beta will go through a certain thickness for the plastic, but if you have any disparities in the thin film, then not the same amount will go through. Like if you have a thin film with the detector that's supposed to let only 50% of the beta go through, but then now it's 52%, maybe out of spec. So this is primarily for that. So
along those lines, I somehow missed what the use for this precious 100 milligrams of Californium that you make is.
They can start reactors, right? It's a neutron source.
So neutron source.
It's a neutron source, yeah. Californium-252 is it's a neutron emitter. They also can have they check concrete and large, like for bridges. I think that's disparities in the concrete.
So this is for analysis.
For yeah.
Neutron activation or something. Some sort of thing.
No, not activations. They start nuclear reactors with those. There's enough neutrons, and so the ORNL sells it by mixing it with palladium and making very wires, and it's by the inches. They sell it, certain amount of inches is so much milligrams of californium, and
they sell that to whom?
there are two companies, Frontier, I think is one of them, and QSA, I think, are the two.
No questions? All right. Present you with this copy cup so that you can, when you drink coffee, you can remember your experience.